Welcome to the final session of our Route 53 Masterclass. Today, we are looking at how traffic is actively orchestrated across global networks. We will deconstruct 5 specific mechanisms: capacity weights, network latency, user geography, client IP ranges, and hybrid resolvers. Over the first 2 parts of the series, we established the foundations of DNS resolution. We mapped out standard parsing, secured the zone apex using alias records, and defined the active polling constraints required by Route 53 health checks. With those foundations set, we must move beyond name resolution. Our focus shifts to designing intelligent routing policies that distribute loads mathematically and integrating complex hybrid environments over physical transit links. Scaling a cloud endpoint into a globally responsive architecture requires analyzing traffic conditions before a request ever reaches an application layer load balancer. By pushing this logic to the DNS layer, we control exactly how and where traffic flows across an entire global topology. Simple routing returns multiple IPs to the browser, which randomly selects one. Lacking health checks, selecting an offline server drops the request. Conversely, weighted routing mathematically distributes traffic based on assigned weights. With weights of 70, 20, and 10, queries perfectly fragment into proportioned pipelines. This granular, percentage-based control makes weighted routing effective for complex deployment strategies. You can execute blue-green deployments, conduct canary testing by routing a fraction of live traffic to a new version, or balance loads across multiple AWS regions. If a specific resource experiences performance issues, you can halt all incoming DNS traffic to that node simply by setting its assigned weight to 0. If all records within a weighted set are assigned a weight of 0, Route 53 instantly recalculates the pool. Instead of dropping all traffic, the system automatically defaults to returning every record in the set equally. This safeguard is a deliberate architectural choice designed to prevent routing starvation if a configuration error occurs. Network architects frequently confuse network latency with physical location. On the left, we measure active latency from a user in Frankfurt. When the packet leaves, it ignores the geographically closer Asian region and routes directly to the US region, which provides the lower 90 millisecond ping. These results occur due to the physical layout of international fiber optic topologies. High-capacity transatlantic cables can often route packets faster to a distant continent than fragmented terrestrial links can route to a neighboring country. Contrast this with geolocation routing, which enforces strict boundaries by continent, country, or state. A specific match overrides a broader match. A packet from Munich routes strictly to the U-Central-1 endpoint. If a user queries from an unmapped location, a default fallback pathway safely resolves it. You must choose the priority for the workload, either optimize for the lowest network ping times across the internet backbone, or enforce strict adherence to regional licensing and data residency constraints. Geoproximity routes traffic using physical coordinates, utilizing a parameter called the bias value to dynamically distort routing boundaries. Watch as a positive bias applied to the US West region physically expands its circular boundary eastward, overriding baseline logic and pulling central state traffic to the western endpoint. Implementing this level of global topography carries a specific operational requirement. You must utilize Route 53's traffic flow visual editor to map out and deploy these geoproximity rules. Dynamic bias scaling allows network architects to shift global load during regional capacity events. You can gradually drain traffic from an overutilized region without relying on sudden, disruptive hard DNS failovers. Beyond mapping the physical location of users, we can control traffic logic by inspecting the origin characteristics of the client itself. This side-by-side grid outlines IP-based routing. On the left, we define a CIDR collection, which maps known client IP ranges to specific endpoints. When Route 53 receives a query from a specific subnet, it matches the CIDR list and routes the query directly to a localized private endpoint inside a peered VPC. By identifying known corporate subnets at the DNS layer, you can route that specific traffic exclusively over private network links, minimizing public internet egress costs and improving lookup performance. Now look at Panel B, which illustrates multi-value answer routing. This policy distributes traffic across multiple independent public resources. An incoming query generates a raw list of IP addresses, but a visual filter scans their health status, removes the failing nodes, and outputs up to 8 healthy records. Contrast this behavior directly with the simple routing limitation we analyzed earlier. By integrating with health checks, multi-value answer ensures that the multiple IPs returned to the client are available to receive traffic. However, you must observe an architectural boundary here. Multi-value routing operates strictly at the DNS layer. Returning multiple filtered IPs to a client browser will improve baseline availability, but it cannot track active sessions, perform dynamic connection pooling, or replace the deep application layer inspection provided by an elastic load balancer. The enterprise reality is hybrid DNS, where name resolution must cross between isolated cloud VPCs and physical on-premises environments. This transit schematic shows how we bridge those environments. While a VPN or Direct Connect provides the physical path, we require Route 53 resolver endpoints to act as the logical bridges sitting atop those links. An inbound endpoint is a mechanical deployment inside your VPC. AWS provisions dedicated elastic network interfaces into your private subnets, configuring them to listen for incoming queries on port 53. When an internal DNS query for an AWS private hosted zone leaves the on-premises server, it travels across the VPN link and targets the inbound endpoint. The endpoint receives the packet and hands it to the native Route 53 resolver to secure the internal IP mapping. The reverse flow is managed by an outbound endpoint. For this direction, you configure Route 53 forwarding rules designed to intercept cloud-originated queries that target your internal corporate domains. If an EC2 instance attempts to resolve an internal corporate hostname, the query is intercepted by the outbound endpoint. The endpoint pushes the packet back across the transit link and delivers it to your local enterprise DNS resolvers. Deploying paired inbound and outbound endpoints establishes a centralized two-way DNS topology. This architecture scales across enterprise footprints and eliminates the need to manage self-hosted BIND server clusters. This flowchart represents the completion of our 3-part systems engineering series on Amazon Route 53. We have now built a complete DNS architecture from the roots up. In Part 1, we mastered standard domain parsing and used alias records to bypass CNN limitations, securing the zone apex. In Part 2, we established reliability by setting up active health polling, defining consensus thresholds, and integrating CloudWatch alarms for our private VPC resources. And today, we orchestrated complex routing variables like bias scaling and CIDR IP control, resolving traffic across secure hybrid endpoints. Combining these distinct logical edge layers provides the tools to build systems that are globally optimized and resilient to regional failure. This architecture ensures that traffic distribution is governed by network health and data, rather than distance or randomness.